Okay. Hi everyone. Good afternoon. So, can you just confirm if you can hear me and then you can also see my screen?
Yes, able to hear you and as well as I am able to see your screen.
Okay, great. Okay, fine. Uh, Fine. So, let's start. Okay. We are 6 minutes into the meeting. Uh, okay. Let me add people. Yep. Okay. So, hi everyone. Good afternoon again, and thanks for joining. So this particular session, before starting, I just want to give my intro. And so my name is Kumar Sawant. I have like complete 14 years of experience in automotive plus uh, embedded systems. So I have worked with software, hardware, uh, and product development. Okay. So currently I run a company named Subbits. We design and develop embedded hardware for industrial clients. The purpose of this particular session is that I've been taking a lot of interviews from couple of years, and I found that there is a gap between what exactly industry needs and what the fresh graduates have knowledge about. And what I think is mostly lacking is the basics, which are not clear. So I have taken interviews of people who have done the PG diploma course from the institutes. Still, I could see there is a lot of gap because even colleges are not making people understand the basics, and the courses are not, I think, able to help the new generation of engineers to understand the basic. My fundamental belief is that if you know the basics of your field, core field, uh, then it's easier to understand the higher level concepts. Okay, but the current education system is making other way around. They are trying to teach AI and other top level application then instead of teaching the level application. So this is just out of my hobby. I'm starting this sessions. Okay, so yeah, so that is the purpose. There is no formal structure to this training. Okay, there is no presentation. We'll be learning together. So the fundamental is different here. I'll not be teaching. We'll be discussing. Okay, through discussion, we'll learn. Okay, this is what I want to try. Okay, and see if it helps people. Okay, otherwise there are courses available in the market, so people can take those. Okay. Uh, so the structure of training is simple. We'll start with the understanding microcontroller, and then we'll see uh, and we design our own microcontroller. So while designing, we'll have some questions, and based on these questions and the understanding of current technology, we'll try to build our own controller. And based on that, we'll also able to solve a lot of questions what we have and which are not actually uh, taught in uh, the college, right, or even institutes. Okay, so let's start. Okay, so first thing is we want to develop our microcontroller, right? So let's start in the basic. So why microcontroller, right? Even microprocessor. So we have so this has been being developed from last almost 60, 70 years. It's not that long of a history. People were doing like relay based logic, correct? So there was some inputs, okay, and then based on that input there was some logic, okay, and based on that logic some LEDs were relays, okay, were getting fired. So it was very simple electrical analog system which were working, and this was like 60, 70 years ago. So but as we developed, made our system complex, eventually we had to go with some kind of a complex system, that is like we came up with a microprocessor, a microcontroller, right? So take an analogy. So now we'll start designing our own microcontroller, which does these things. Okay. So to take an example of a PC. So everyone knows about the computer or laptop. So what laptop has? It has a processor, right? Then it has RAM, okay, and it has a flash, or we can say it has a hard disk, okay, and then we have a keyboard as a inputs, okay, then we have a memory, sorry, a monitor as a display, right? So this is what a complete computer it is, we have, okay, but it's a complex system. So okay, so now we would like to make our own microcontroller. Okay, I'm not going to go into that basics like why we need microcontroller. Okay, what are the basic building blocks? We know, and but we want to see why we need those basic components, right? So let's design our own microcontroller here. So take an example. This is a block diagram of a microcontroller. For sure, we know microcontroller has some inputs, some outputs, right? And out of those, some inputs are like reset input, then we have a power, okay? So these are like basic everywhere, and then we have a ALU, right? And everyone knows ALU is like arithmetic logic unit. ALU is like a brain of our system, okay? Which like does some kind of a uh, processing and the instruction what we give, okay, and then gives output like it will toggle the pin here, right, or it will monitor the pin, and then based on that it will toggle. But to do that you have to write a program, right? So we have some kind of a memory block here, right, to store the program, okay. So we'll just for now we'll just call it as a memory, okay. So to talk with the memory, so there is a ALU unit and there is a memory unit in your MCU. So to talk with the memory, you need some kind of a wire, right? Okay, and that wire can be a single wire, but if you have a single wire, what will happen is you will communicate in a serial bus, right? Like this. But the problem is if you do this to transfer 8 bit of a data, so you have 1 2 3 4 5 6 7 8, you will need suppose one clock cycle takes about 1 millisecond, so it will take 10 millisecond to get the data, but you want system to be faster, and as we know mostly parallel bus, okay, or parallel communication is faster. So in that case we have a number of wires coming from ALE to memory, and that is what we call as a bus, okay. So we'll leave this bus concept here. I just wanted to show you that from ALU to memory the communication internal is not a single wire, it's a bus, okay, just for the sake of making it faster. Now let's dive into memory. So we need memory, that we understood, okay. So what kind of memory, okay? So we have two types of memory. We have as we talked about in the initially here, that we have two kind of memory. One is RAM, one is hard disk, okay. So in case of a microcontroller we have two choices, okay. I'll give a choice as an assumption that we have a RAM, okay. So RAM and a ROM. So RAM is a random access memory, okay. ROM is a read-only memory, and then I'll make a asterisk here. So we say it as a like read-only memory. It's not read-only because someone has to write something there first. Then only you can read it back, right? So I'll make asterisk. And RAM is a random access memory. So we'll have a properties of these things, okay. So there are some properties. We'll write down those properties. What are those properties? Okay. First is volatile or non-volatile. So RAM is volatile, okay, and ROM is a non-volatile memory, okay. So what is volatile? So simply, like if you turn off the power, the data of the RAM will vanish, right? So whatever you have written, it will vanish. And then we have a non-volatile. Whatever you write will be persistent. So persistent means it will stay there. It will be part of that memory even after you turn off the power to the memory, right? Then the second properties of the RAM is, or this particular kind of memory, this is faster. Okay, so this is very fast. Okay, and this is slower. Okay, so RAM is faster. Okay, faster in what sense? Faster in sense read and write. So if you want to read and write RAM through ALU, it will be faster because there are some. Uh, so you can't directly actually write from ALU. There is a one memory control unit. So I'll just draw this here. So that is a memory control unit, okay, which does the write and read from the memory. Okay, so in case of RAM, it is faster to read and write things. Okay, and ROM is way slower because if you write to the RAM, you have to give a wait states. Sorry, to ROM, and you have to give a wait states. After waiting only, and some after some time, the data will be written to ROM. Okay, but you can read faster, but write is slower. Okay, and then we have a third property is a number of writes. Okay, so this is almost, I would say, this is infinity. Okay, not practically, but ideally I'll say this infinity. So you can have a number of writes to the RAM as infinity. You can write any number of times. But to ROM you can write as again. That's why I had asterisk here, right? So ROM you say read only memory, but that does not mean you can't write it. Okay. Uh, the thing is you can write ROM, but you can write it a limited number of times. Okay. So limited number of writes. Okay, so those are like if you check any data sheet of any ROM, okay, or flash, I'll also call this a flash. This is a common term in case of embedded. Okay, so in flash, okay, you have a number of write cycle which are limited, and those are like if you read the data sheet, they would write it like a 10 kilo cycles uh, minimum. Okay, so they advertise is like, okay, minimum 10,000 times you can write it, but after that it's up to the uh, like that particular memory, manufactured memory, you can write more than that, but the OEM or the chip manufacturer will not take the guarantee for that. Okay, so and then you have a fourth parameter is a byte-wise write or not. Okay, so I would say write minimum write size. I would say write size. Okay, I don't remember the exact technical word for this, but okay, minimum size which you can write. Okay, in case of RAM, you can write a single byte at a time. Okay, but in case of ROM, the problem is you can't write a single byte. You have to, so the ROM is divided into sectors. So I'll cover that part also, okay, after this. So you can't write a single byte. You have to you have to write a in a sector wise, sector write. Okay, so you understand the properties of this RAM and ROM. Okay, anyone wants to add any property which they know and I have missed? Okay, great. So we said faster. We'll add one more thing that is that's not actually that important, but that is the cost is higher. Okay, this was taught in college a long time ago. That's not a valid right now, but still it's not that cheap also. So cost of a ROM is less, on a less side. Okay, so now we write down the properties of RAM and ROM. Okay, so take an example. I want to store a code. So you, as I understand that you are from the electronics background mostly, so you know that when you write a code, you get a hex file and you have to store that hex file in the memory, right? And that hex file, that code of your, which is converted into bits of a machine code, okay, uh, that needs to be what? Persistent, correct? So that needs to, after like you turn off the power to the controller, the code should remain in the memory. So in this case, who wins? Definitely, you need ROM for that kind of a feature of your microcontroller. So you will use this property of a ROM, right? So let's make this asterisk here. So we will use ROM for this. Okay, and this is where RAM fails. Because the data vanishes, so you can't use RAM in this case to store a code. Okay, uh, ROM is slower. Okay, RAM is faster. So here, like RAM wins. Okay, it's faster. But why we need faster? That we'll see later on. Okay. Then number of write cycles are infinite. Okay, so in case of even program, you download a program into your controller, you don't have to write it multiple times, right? You flash it once, and then for mostly production, in development time, you definitely you program your flash multiple times. You change the code, program, test it, change the code, fix the bug, change the code, flash it, and or program it and test it. In that case, definitely you don't care about how many number of times you have to write, because you will definitely write less than 10K. Okay, so in this case, for storing a program, definitely ROM wins. Okay, but RAM has a definitely advantage where it has a uh, like infinite number of writes. So definitely you can see somewhere it is used. And then write size, so you can write access, so you can say you can access 1 byte at a time for RAM, so to write. But ROM, you can only write a complete sector at a time. So I'll, after this I'll just cover that section. Okay, so definitely writing single byte is important. Okay, and RAM actually wins here because you don't have to delete the complete sector and write it. So let's jump onto the uh, how memory works actually. Okay, any memory, ROM and a RAM. Okay, so basic structure of a memory. So I'll just draw this as a memory. Okay, so memory has any kind of memory. Even you see like a 32-bit memory, it is always divided into what? A 8 bit of a section. So each section, okay, so each section of any kind of a memory is always a 8 bit. So, and that is what we called as a single unit. Okay, unit. And then each section of a memory has an address. Okay, so this is address 0, address 1, 2, 3, 4, and so on. Okay, so and when I say RAM, you can write a RAM in a single byte. So that means if you want to write something from ALU, like a variable X, which is of 1 byte, okay, you can directly write X here. Okay, and then you have a Y, uh, which is like again 1 byte. You can write it here, and then you have a Z, which is 2 byte. You can write Z1 and Z2, right? So that is like a two parts of Z. You can write Z1, Z2, and then it's simple. Okay, you can write. And then suppose you want to update X again. So X initial value of was 0, and you want to write 2. Okay, from the ALU, the ALU can directly instruct RAM, and then the RAM only X value will change. So if Y is like 3, Z is like 0, and so it will not affect this. Okay, so that's how RAM is faster. You can, because you can write RAM in a single byte. But similarly, if you take case of a ROM, as I said, ROM is always divided into sectors. Okay, so individually, if you look at it on top, it all, so let's make it RAM, and this is a flash or ROM. Okay, so you have memories here, single byte of memory. Okay, but the memory even address is similar, like 1 2 3 4 5 6 7. But if you look at the data sheet of ME memory, okay, you will see it is segmented. So they call it as a page size. So for take an example, our flash is a 4 byte of a sector or a page. Okay, so that means if I am so previously suppose x, y, and z was stored here, x, y, z1 and z2, some memory data was there, and I want to just update x, okay, from value 0 to 2 in case of flash. You can't directly go and write x. What happens is, as I said, you can't directly access memory. There is a memory control unit, okay, around us inside a microcontroller. So if you go give access 0, address 0 to write to, what it will do is first it can't write directly to, it has to delete complete sector or a page and make the values to all ones like FFFF. Okay, and then only it can write value to address 0. So that is how flash works. So you have to, so in simple terms, write, if you want to write something in flash, it's the first action is delete. So internally memory unit will delete complete sector, okay, and then only it will write the 2. So what ALU has to do in this case now, because he has to preserve the value of y and z, okay, so it has to read first value of address 1, 2 and 3 and 0, okay, store into RAM or any internal memory, okay, and then erase this and then again write complete values, like it has to write x again, x, y, z1 and z2 back to the memory. It takes time, it is not a good thing to do. Okay, so okay, so in this case if you see, RAM has a definite advantage here, so you can write in a on a single byte and read faster. Okay, so to design our own microcontroller, what we have to do, okay, we store program, okay, that is hex file. We said okay, hex file has to be stored in the non-volatile, so that for that we need a ROM. But after ALU executes the value, okay, or certain operations, it has to store the temporary data in some temporary memory, okay, or some memory. In that case, definitely RAM is a best contender, because as we see, even it is a volatile, it is faster, you can write multiple times, okay, and you can write at one byte at a time. Okay, so what we can do is, we can divide our memory into two. Okay, we can say RAM for execution, okay, and ROM for program storage. Okay, so now we understood, right, why we need two different types of memory, because one certain type of memory can't fulfill our requirement to make a good controller. Okay, with ROM also we can make a controller, but it will not be faster, and after like 10k cycles of write, uh, 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 it will go bad, right? So in this case, that's why we need a RAM and ROM in our memory. Now let's elaborate on this. Let's draw a controller, microcontroller again. Okay, so we said we have a ALU here. Okay, so what ALU has? ALU has some kind of a processing unit. Then it has some internal memory blocks also, that we call this as a registers for a temporary thing. Okay, now we said based on our current assumption that okay, we have a flash and we have a RAM. So we divide into now two different sections, RAM and flash. Here we store program and here we store or we don't store anything, we execute from this. Okay, now when controller powers up, you provide a power. Okay, so ALU has to, because it's your brain. As you wake up, the first thing you open is your eyes, right? And then your senses start. So similarly, it is like ALU will need to know where to start. So it will just, for now, we'll assume it has to communicate with the flash. But to communicate with the flash, you need to address the flash. So what you need is the address bus. Okay, so from address bus, you have to, and this is a, like a bus, you have to provide the address to a flash. That is a so if suppose your flash is like a 16 address is 0 to 16, 0 to 15, you will need a 4 bit of a, or 4 line address. Okay, because it will go to 0 to 15. Then to, and the address is unidirectional. I made it wrong here. So address is unidirectional. From here, it will uh, give address to the or ask for the data from particular address, and then ALU also has a data bus. So what will happen is, if you give address 0, so what flash controller will do is, or memory controller, get the data and then push it on the data bus. So what will happen, all on the 4 lines of this, or 8 lines definitely. In case of 8-bit controller, the data bus size is 8 parallel lines. Okay, so whatever 8 bits you had here, like 0 0 0 0 1 1 1 1, will be presented on this particular data bus, and this data will go to ALU, and ALU will do something with it, right? To take an example, I have instruction here in program. A, sorry, C is equal to A plus B. And the value of A is written in the flash only. So value of A is at some location, that is 5. Value of B is at some location is 7. Okay. And what it will do is, the first instruction is add. So the ALU will get the instruction. Okay, so that, okay, there is an instruction to add. The next, it will go to next address. Okay, value of A. So it will store A here. Value, get the value of B, store here. But then what he has to do, store the value of C. So for that, what it will do, it will communicate with the RAM. So for communicating RAM, you need again, sorry, address bus, and then you have a data bus, right? Again, 8 bit of a data bus. And then you can do is, give a write instruction to RAM, and then you write the data at address 0 here and store C here. Okay, and whenever you want to read back the C, you can just give a read instruction to the memory, and give address, and then the address data will be available on this port. Okay, so this is where we assumed the address of this is starting from 0, okay, and in and ending at something X or Y or Z. Okay, in this case we need two different address buses and two different data buses. Okay, so there are two architectures of memory, sorry, controller, that is von Neumann architecture. Okay, von Neumann architecture, and there is, I don't remember it, uh, there is another architecture. Okay, so one of this is this, and then take an example here. What we are wasting is, we are wasting a buses. Okay, so mostly in controller, what we do is, instead of having a two different address spaces, so this is called address. 0 to X is one address space, and 0 to 15 is the second address space. So instead of that, what we in the microcontroller we do is, I'll show you that in a couple of minutes, if I get the data sheet. Okay, uh, so what we can do is, we can have a single address space. Okay, and this is a memory controller, and inside memory controller we'll have a RAM, and we have flash. Okay, and the ALU will directly have one address bus and one data bus. But in that, if you do this, what happens is, you can't have a same addresses in RAM and same addresses for flash. In this case, what we, the memory controller does, so 0 to X is 1, and then sequentially the flash address is X plus 1 to Z. Okay, so in this case what we are saving is number of address lines and number of data lines. Okay, so if I can get this memory structure, yeah, memory mapping. So let's open this. Okay, so this is the memory map for STM. You can see is from address 0 here the code is starting. Okay, and then at address like some 0 to 0x2 SRAM is starting, and you can see here also the flash is also, or code memory is divided into multiple sections. Like there are some settings microcontroller stored, then your flash memory where you can store your program, then you have system and some option bytes, and then RAM if you look. Okay, so RAM there is nothing, and then there is a peripheral uh, so you have a peripheral registers. Okay, which you want to store. Okay, and here we have vector table. Okay, so any questions till this point? Okay, if you have questions you can just type in, not a problem. Okay, so okay, let's continue. Right. So we talked about first, okay, just recap before you go forward. We talked about, we assumed that a microcontroller has a ALU. Okay, that is the first, like it's like a processor, which is a brain of a controller. Then, but brain needs to have some kind of a program to execute something. Okay, so to store program we need memory, and to which kind of memory we discussed about RAM and ROM. Okay, there are two types of memory available in the market, the properties of both. Okay, and to store, and then per particular purpose of microcontroller we need both. We need persistent memory to store the program which we write, and we need execution memory for temporary storage. And we figured out, okay, ROM can do that stuff, so we have a RAM to do that. So we figured out we need both the memories. In the case RAM, we need more ROM, definitely, because program is bigger. Even if you take example of your control, your PC, you have a bigger hard disk like in TBs right now, but you have a smaller RAM. Okay, like now it is like 16 GB or 8 GB. Right. So similarly, microcontroller, we do that. Okay, we understood how the memory works. Uh, the one byte, and then how the addressing is done. The difference between RAM and flash in case of how that is written. Okay, so you will learn, like hear about, I just remembered, you will hear about two terms in case of flash memory, that is a NOR flash, and then you have a NAND flash. Okay, you can research on your own, but it's simple if you want to. So this is a single section of memory, that is 8 bit, okay, of a ROM or flash. So this so in case of a I think NOR or NAND, you can't directly write, suppose you want to write 0 0 or 0 1 0 1 0 1 0 1. Okay, okay, so you can't directly write 0 1 0 1 0 1 0 1 0 1 here. Okay, uh, the bits has to be 1 first. Okay, so suppose initially it was 1, then the memory controller wrote 0 1 0 1 0 1 0 1, and now you want to write 1 1 1 1 0 0 0 0. Okay, so memory controller can't directly write 1 1 1 1 0 0 0 0. First it has to erase it. Okay, so it has to erase means it will make it 1 1 1 1 again. Okay, and that is how you can, uh, after only everything is 1, then only you can write zeros. So it's simple, like you can't write ones, you can only write zeros. To make it 1 you have to erase it, and that's the time delta t takes in case of a flash, because now you have to have a erase cycle which takes time. And then again I said erase cycle cannot be done on a single byte, it has to be done on a sector size. So it can be 4 byte, it can be 12, 1 kilobyte, it can be 2 kilobyte, or it can be almost 8 kilobyte. So depends on which kind of a memory. So you have to go into data sheet, and figure that out. Okay, so based on that only you will understand, and I think here you can see if I hmm, yeah. So if you look at the data sheet again for flash, you will see program time is store time. Okay, and then page size is 2 kilobyte. Okay, so at a time you can erase and write 2 kilobyte, not less than that. And how much time it takes? 20 milliseconds just to erase a page. Write is faster. Okay, like 50 microsecond, but erase takes time. Okay, so that's why as we said, flash the flash is slower in case of a writing, or rom is slower in case of writing. Okay, so this is about memory. So let's jump on to the part where how this thing gets executed. Okay, so we'll talk about the reset. So next point of the training was before main what happens. So we know, like we are all engineers, we know like first function which is being called is main. Okay, uh, in case of a like C programming, but it's not true in case of a microcontroller. Okay, so microcontroller, take an example. If I have a code, okay, in a C file, all right, some main.c, and then I have some void main function, and I am in main, I am doing like a or c is equal to a plus b. I'm executing this, sorry, b plus c, a plus b, and then I am doing c plus plus, something like that, right? So mostly people assume that main is the first function which is called. Okay, but that is not true in case of microcontroller. So why it's not true, I will tell you. So whenever you create a hex file, so you I'll take one more session if needed. I think that is about the compilation process. Okay, for now just assume something. Okay, compilation process. So how from .c to hex file, how everything happens from the preprocessor to compiler to assembler to linker, exactly on compiler level, how the symbols are created, how the memory is assigned to variables, functions, that I'll take a section. If you understand that, you understand everything. Okay, so that is the, I would say, holy grail of how the system works. But before that, let's understand. You have a hex file. Okay, and then hex file you have a, like instructions, right? So everything once was instructions, and then instruction, and you have somewhere your main function has been assigned the address. So even if you look at the there is a file, I don't know people know about this. Let me see if I can find that also for you guys. So yeah, so here you have a map file. When you compile your code and generate a hex file, you will get a map file, right? And if you open that map file, and this is where you find the addresses for everything. So you can find the address for main function. Okay, and I don't know where. Okay, so we will have somewhere, yeah. So this is the address, exact address where the main function is stored, and this is not zero. Definitely, I think people assume that main start at the zero address of a flash. No. Okay, so it's stored the main function, and for this particular is stored at some address. This is like A290. Okay, so if you go back to our discussion, the hex file has all the functions and variables instructions stored, and main is something like right now we said A290 somewhere here. Okay, when you program this hex file in your memory, again the main function call will be here somewhere. Some, as I said, like A290. So how does the ALU knows from where, which instruction, which address the main should start? It does not know. Okay, so what happens is, so everyone I think knows about vector table. Okay, okay, and NVIC in case of ARM. Okay, nested vector interrupt. uh, okay, so this is again like a memory control unit, and the ALU, this is one more module which you have in a microcontroller. Okay, so all the interrupts, like take an example of reset, take an example of UART, all go through this NVIC. Okay, so and I'll put one more point, and that is add one more new concept, that is vector table. So Flash has a vector table. Okay, so that is a hard coded thing, and it can't change. It is the microcontrollers guys have added that into this. Okay, I need to check in the data sheet if I can see vector table. Okay, but mostly the vector table is at address 0. Okay, or at the top of a bottom of a memory. Okay, and it has a addresses, fixed addresses. So reset will have a 0 address, assumed. UART will have a address 1, and then I would say, like take an example of external pin interrupt, will have a address 2. Okay, so what happens is when you turn on the power, what you have to do, you have to also give a reset input, right? Otherwise the controller will not power on correctly. So when you give reset, the NVIC will figure out what kind of interrupt it is, and it will tell the ALU, okay, that I have a reset interrupt which is occurred. When the reset interrupt has occurred, okay, what happens is ALU knows, okay, if the reset interrupt there, I need to execute instruction from address. So if there is a reset interrupt, so ALU knows I have to execute instruction from address 0. Okay, so at address 0, what we store the address for a next instruction, and it can be main. Okay, so you store the address of A290. Okay, so if you store A290 here, and that has happened, even that happens in the code, I'll show you. No, mostly don't, right now people don't know about it. Okay, let me open my STM studio. We'll talk about that later, but okay, just assume that or understand that, okay, whenever you power on, NVIC looks which interrupt has occurred, and based on which type of interrupt, it will pass on that interrupt type to ALU, and based on interrupt type, ALU know to which address it has to jump, and that address, when you compile and create your hex file, okay, in your hex file, if suppose address 0 is here and address 1 is here, it will have a reset address, that is go to A2, it will stored like A290, and that flash image is stored into here, and then when the ALU knows that it has to go to the reset address, and reset address is 0, it will go there, fetch the address, and next instruction it will jump back to the main function, and it will start executing from here till the next. Suppose while executing from main, UART interrupt comes, so an EVIC will tell the ALU that, okay, stop whatever you are doing, there is a UART interrupt. ALU knows at which address the UART interrupt table is, so it will go here. Here you have a function for UART handling, okay, somewhere at address 10. So here it is stored 10. The ALU just fetch the address and then jump and start executing from UART. Okay, I know this. I think this might be, I'm going to slightly faster, but just for your understanding and high level concept, I'm showing, and this all the information is available. I think on YouTube you can get it, or there are a lot of material available on how this works. Okay, many of you people might know about this also. Okay, so I'll just show you where I was trying to system. Just give me a minute. So, in case of STM, you have the startup file, okay, and you can see, okay, here you can see, so this is vector table and each word is actually address. So this is address 0 1 2 3, and which function to call or which address to jump, it is actually given here. So if you see the reset handler, and if you jump into reset handler, it says assembly code, and at the end of the assembly you are actually calling main. So that assumption that we first call main after reset is wrong, okay, and why it is wrong I'll take a separate session on it later on, but the first function is not main, okay, as most of the like uh, IDEs, okay, or tools, when you create a project they give you basic structure, and that basic structure everything is predefined. That's why we assume that the main is the first function. No, as and even I said here for just simplicity purpose, when the reset vector occurs, the ALU will jump to address 0, and address 0 we store the address of main. No, we can do that, but we don't do that. We actually store the address of this reset handler, this assembly function, which has been written by the STM people. What it does, it's clears the RAM, it's to copies the static variables to the data section. So if you can see it fills the BSS sections with 0, okay, copies the data variables, which the variables or static variables which initialize value into particular RAM addresses, okay, initialize this the stack pointer. So all this is done. After that it jumps to the, and then it does the clock initial. Even this function you might not know, right? So it does this also, okay, and then after done doing that, it goes to and calls the main function, okay. So that is how the execution happens, and that is why the NYC and the interrupt handler is very important, and without reset your controller can't start properly, because your controller ALU will not know where to start. So hard reset, or the and this is what we call the hard reset from external pin, based on which the ALU will start from 0 again and initialize everything and start executing your code. Any questions till now? Okay, and now we'll go into, and this is what question I ask in the interviews. People don't answer it correctly. You have a 8-bit controller, right? And then you have a 16-bit controller, and then we have a 32-bit controller, right? So when I ask people, okay, what is the difference between this? Okay, why we call it as a 8-bit controller, why we call it as a 16-bit controller, and why we call it 32? And everyone knows that 8-bit controller is slower, 16-bit is faster, and 32-bit is more faster. Okay, so the reason I'll tell you why. Okay, so mostly people previously used to work with 8-bit variables, right? So everything was 8-bit. Then the system becomes complex. People started working with 32-bit data or 16-bit data, or initially 16. So you'll see the development of a microcontroller is like this only. They started manufacturing 8-bit, they figured out it's slower, then they started with 16-bit, and then they went to 32-bit. They never jumped from 8 to 32. They 8 to 16, then again figured out that 16 is slower, and they went with 32. I'll tell you why. Okay, this is interesting. So as we said, we have memory. Okay, and through ALU, okay, we are accessing this memory, and each memory is of a 8-bit. Okay, so take an example. I have a X variable which is 8-bit, Y variable which is 16-bit, and Z variable which is 32-bit. Okay, and this is a, assume this is a 8-bit controller first. Okay, and what I want to do is I want to have a Z uh, and X plus Y, Z is equal to X plus Y, something like that. Okay, so and my x is stored here. X is 8 bit, y is as 2 bits or 16 bit, it will be like y1 and y2, and z is as 4 bit, it will be 4 byte, it will be x z1 z2 z3 z2 z3 and z4, right? Because you can store 8 bit of a data in one memory section. Okay, to simplicity we'll just consider the RAM thing and we'll forget about ROM and then ALU. And then we have a data bus or address bus. Okay, so address bus depends on how much address you have, right? So if you have 8 2 raised to 8 bit of address like 256, okay, lines or memory section only, you need 8 bit to address it. If you have a 2 raised to 16 bit range or address range, then you need a 16 bit of address, but is nothing to do with the size of or we when you call 8 bit or 16 bit, nothing to do with the memory bus or address bus. Now take with the 8 bit controller, what we will have we have is 8 bit of a data bus. Okay, so I'm doing here what, z is equal to x plus y. So first I need to fetch x. Okay, so we'll send 0 here, fetch x here, and then I'll copy x and keep it here in one of the registers. Okay, so register 1 I copied and keep the x. Then I want to read y. Okay, but to read y, as I can only read 8 bit at a time. Okay, what will happen is I just have to first give 1, get the data y1. Okay, then I have to get the data, again send the address. Okay, I need the data from 2, get the data y2. Okay, then do masking and shifting and then make y as a fixed big 16 bit variable. Okay, then I do x plus y, and now I have a z which is 32 bit, and in single instruction I can't write 32 bit because my data bus is 8 bit only. Okay, so what I have to do, I have to give 4 instructions. First store z1, then z2, then z3 and z4, and that is 4 write cycles. Plus, to store this I have to first divide this 32 bit into 88 bit masking and shifting, right? First I have to upper 8 bit, I have to mask, shift it to lower bit, send it to z as a z1. Suppose this is z1 2 3 4, and then I have to mask 2, shift it by 16, get it here, and then send it here, and then with the z3 I have to mask it and then shift it by 8 bits and send, and then so this masking also takes time. So if you want to work with 32 bit 16 bit variables in case of a 8 bit controller, you are taking lot of time. Okay, that's why the system is slower with a 8 bit controller. Okay, and to bypass this or to upgrade this, what we can do is we can change and make the system as a 16 bit bus. Okay, and that's where 16 bit come, but the problem with 16 bits is you create a padding. Okay, so padding is the concept, I think you can learn on your own. You just go, and I have given you the where to start. Okay, and how to think and how to learn about this, right? And you can now understand how 16 bit works. Okay, but the problem with 16 bit is, suppose I want to read 0 at from address 0, right? But my data bus is 16 bit, so even if I give 0 and get the address or value of x, I will inherently get y1 also. So that is a problem with now 16 bit, because I just wanted 4 bit 8 bit of a data, but as the data bus is 16 bit, I'll also get y1, and then I have to cancel y1 and store x. So that is a problem with 16 bit, and how that is resolved, that comes with the padding and how to make the even 16 bit efficient. And the same problem is what 16 bit, because now to store z you still have to have 2 write cycles because it's 32 bit. So to make it faster, we went with the 32 bit, but where you can write 32, but again it's a problem. Okay, so they uh, to make it efficient, compiler adds padding in the memory, and then you can learn about it. It's a very interesting concept. Okay, any questions till now? Because we are actually at the end of the time. I think I have covered what I wanted to, and I don't know. I know if it is was helpful for you guys. This is the first time I'm doing this. If it is helpful, let me know. I'll plan something if I get time. Okay, if there are no questions, I think we can close. Okay, is there a chat? I think is there are there messages? Okay, okay, no. Uh, okay, what is the lifespan of a typical flash memory device? It depends on how many writes you can do, but I think that's where when you store data into memory, okay, that is very important. Uh, so you, as I said, you can write into flash, and there are scenarios where we do write user settings in the flash. So suppose you have a, in case of your tablet or phone, you change the setting and you store it, or volume setting or some setting, and then you store it, and it is, you want to retrieve it, you don't want to that setting to be vanished after power off. To do that, while runtime you store into flash, but uh, as I said, it's a limited number of write cycles, so we have to be very cautious when you write into flash. Okay, fine. If nothing is there, thanks guys. Thanks for your time. Okay. If you have any things, you can just post it on the LinkedIn page. My team will look into it. Okay. Thank you. Have a nice day. Bye.
Thank you.